Hello and welcome everyone. My name is Dane Menke. I am the Digital Marketing Manager here at REGENESIS and Land Science. Before we get started, I have just a few administrative items to cover. Since we're trying to keep this under an hour, today's presentation will be conducted with the audience audio settings on mute. This will minimize unwanted background noise from the large number of participants joining us today. If the webinar or audio quality degrades, please try refreshing your browser. If that does not fix the issue, please disconnect and repeat the original login steps to rejoin the webcast. If you have a question, we encourage you to ask it using the question feature located on the webinar panel. We'll collect your questions and do our best to answer them at the end of the presentation. If we don't address your question within the time permitting, we'll make an effort to follow up with you after the webinar. We are recording this webinar, and a link to the recording will be emailed to you once it is available. In order to continue to sponsor events that are of value and worthy of your time, we will be sending out a brief survey following the webinar to get your feedback. Today's presentation will discuss PFAS criteria in groundwater. With that, I'd like to introduce our presenters for today. We are pleased to have with us Jeff Hale, Practice Leader Emerging Contaminants at Woodard and Curran. Jeff provides consultation, strategy, and direction for challenging environmental and natural resources issues with emphasis on PFAS, emerging contaminants, complex sites, remediation, liability management, and environmental forensics. He is a thought leader for emerging environmental issues, having served on expert panels and chaired multiple working groups on environmental issues ranging from hydraulic fracturing to emerging contaminants. Jeff's core technical expertise includes contaminant hydrogeology, fate and transport, and fractured bedrock characterization. We're also pleased to have with us today Dr. Kristen Thoreson, Vice President of Quality and Process Improvement at REGENESIS. Dr. Thoreson manages and evaluates the company-wide quality processes and continuous improvement activities at REGENESIS to ensure consistency and reliability in product quality, performance, and service. Prior to this role, Dr. Thoreson served as the Vice President of Research and Development for REGENESIS and Land Science, where she led the development and implementation of numerous products and technologies. Dr. Thoreson is an inventor on several issued patents and is a frequent speaker at scientific industry events. All right, that concludes our introduction. So now I will hand things over to Jeff Hale to get us started.
Thanks for the intro, Dane. I'm pleased to be speaking to you today about the predictability, sensitivity, and practicability of attaining PFAS criteria in groundwater. So the presentation will have three main parts. First, I'll talk about empirical PFAS fate and transport projections. Then we'll use that to show estimating PFAS attainment distances and receptor vulnerability. And I'll also cover statistical distribution of PFAS relative to regulatory criteria. And then we'll wrap it up and pull it together with some conclusions. So the first item is empirical PFAS fate and transport projections. There's been a lot of talk and research about what we know and what we don't know about PFAS, particularly PFAS fate and transport. Some of the information out there is, speculative about the unique characteristics of PFAS and how they might behave in the environment. But we're also accumulating a lot of PFAS data as an industry that are being stored in publicly accessible databases. So I think we've accumulated enough data that we can empirically determine what we might expect from a PFAS plume as far as its behavior and migration distances. And that's what we'll be talking about in this section of the presentation. So as an example, here are a few diagrams of PFAS concentration in groundwater versus distance. On the left-hand side, we have an example from an Air Force base, and the left-hand graph is for PFOS. And we're basically showing the concentration of PFOS versus distance. And on the right-hand side, similarly, this is a graph for PFOA, on the y-axis versus distance on the x-axis. And on the right-hand graph, this is actually an amalgamation of data from 4 different sites, and we've normalized the source concentration for each of those sites to 1 in order to put them on the same graph. And we'll be exploring that graph in further detail as we go. But just as an illustration, you can see that there's a pretty good fit to this function of concentration versus distance for some of these PFAS data from different sites. So the point here is PFAS data sets exhibit predictable concentrations versus distance. So let's explore this a little further. As I said in the intro, there's a lot of PFAS data being collected, especially from groundwater. In a lot of cases, that data is being stored and housed in various publicly accessible databases. So we're going to look at data from the state of New Hampshire as an example today. And the New Hampshire DES PFAS map and database provides a rich data source. So in this example, we have a map from the New Hampshire PFAS database, and the red dots on that map represent the combined concentration of PFOA and PFAS greater than 70 ppt, which is the current EPA health advisory level. Yellow dots on the map represent where individual PFAS may be above New Hampshire's ambient groundwater quality standards for those individual PFAS. And the green dots, fortunately, there's quite a few green dots, but that indicates where individual PFAS are less than respective ambient groundwater quality standards in New Hampshire. So the database includes data for PFOA, PFAS, PFHXS, PFNA, as well as total PFAS. The sources to which these data are attributed include landfills, POTWs, industrial facilities, fire stations, airports, and a former Air Force base. And there are data for a variety of media, including groundwater, surface water, and other. So I inspected this map, zooming in and out all across the state, looking for distinct concentration gradients emanating from a distinct or particular source. And I was able to identify 4 examples where there was a distinct source and a distinct concentration gradient emanating from that source. Is an empirical basis to see what's going on with PFAS migration in the state of New Hampshire. So of these facilities, we've got 3 landfills and a POTW, publicly owned treatment works. And I describe these as what I call end of PFAS life cycle waste facilities. And to the prior point, I think that's important because there's some expectation that precursor transformation at these type of end of life cycle facilities may have already occurred. The other point I wanted to make is every one of these sites had relatively similar conditions, or at least we could infer similar conditions, such as similar physical settings, similar aquifer type, similar source type, and proximity to a water body where groundwater would be expected to discharge. So this is the select group of sites that's going to be the basis for our example. So let me give you a look at a couple of the sites that make up the data set that we will be evaluating. So this is a POTW, and I'll animate what I consider to be the groundwater migration pathway. So we see here we have a source concentration of 838 nanograms per liter. This is for PFOA, and we'll be using PFOA as an example for much of the presentation. But there is a pretty distinctive concentration gradient along an inferred groundwater flow path towards the river that's nearby. Here's an example of one of the landfills that I looked at. And again, we have a source concentration near the landfill, inferred groundwater flow towards a surface water body, and a handful of monitoring wells between the two. So in this instance, the monitoring wells do not fall as cleanly on the inferred groundwater flow path, but there is a discernible concentration gradient in that direction. But to verify and validate that we were looking in the right direction as far as contaminant transport and groundwater migration, I looked at the ratio of PFOA to PFAS here. So PFOA and PFAS have different sorption coefficients. PFOS is more sorptive than PFOA. So as they migrate together in groundwater, their ratio is expected to change with an increase in PFOA relative to PFOS. So this graph shows the PFOA to PFAS ratio for the monitoring wells we just looked at on the map, and you can see there's a linear relationship and a strong fit to the changing PFOA to PFAS ratio that assures me that we were looking along the right groundwater flow direction. And just to further explain that, this is a graph that I like to show. It is the log KOC for a variety of PFAS, so a absorption coefficient for a variety of PFAS. This data derives from ITRC's PFAS technical and regulatory guidance document, and I point out here that PFOS has a higher absorption coefficient than PFOA, thus explaining why their ratio changes as they move through groundwater along the same path. So let's get back into the basis for this example empirical model. And this is a graph I started to show towards the beginning. And again, we're looking at a normalized PFOA concentration for 4 sites versus distance from source. And again, since we're putting multiple sites together with different source concentrations, we normalize those source concentrations to 1. So as I said, we normalize source concentrations to 1, which is C0. The source concentrations ranged from 63.7 to 838 nanograms per liter, and the 838 nanograms per liter was for the 1 wastewater treatment plant, or POTW. As I noted before, this is represented by 3 landfills and 1 POTW, and it gives us 15 samples. So a lot of data in the data set. Like I said, there were 4 sites that I could identify that, we have I really know what's going on here. Distinct source, concentration gradient, can infer a groundwater flow path. So more samples would be better, but I think this 15 gives us a pretty good data set for this function. So just another layer of information with this data set. The red dots represent that POTW site, and you can see it's a pretty good fit, and I would say the POTW data perhaps are the backbone of this regression. It's not a perfect fit. Some of the data points do fall off the best fit function. So I did want to look at, what is the variation and error in the data set we're looking at. So the double arrows are instances where the best fit function underestimates an actual data point, so it would be less protective in reality. And the average of those underestimates is 1.9 times, so almost 2 times the measured value. So, this again is empirical model I think is useful, but it's not perfect, and we need to bear in mind, the amount of error we may be dealing with. So what are the sources of that error or these points falling off the line? Analytical variability and error. Different facility age or history, precursor transformation to PFOA, aquifer characteristics, and geochemistry. But I'd like to assert that for the examples that we selected, we know or infer that they have a similar age. They're similar types of facilities with a similar history. As I said, there's an expectation that precursor transformation would have already occurred. And I think we've got very similar aquifer characteristics. So although those are sources of error, I think these sites are fairly similar, allowing us to basically plot them on the same graph. And just wanted to look at the worst case scenario in this one instance, looking at the double arrow. That's the instance where we had a data point fall off the line by the most, and it was 3.3 times underestimate of the actual data point. And that occurred, 9% out of all the data. So next, we'll talk about estimating PFAS attainment distances and receptor vulnerability. So looking at that graph of concentration versus distance and amalgamated for a number of sites, I think it's interesting, but how do we turn it into something that's useful and practical? So what I did was I took that function and I developed a matrix of outcomes based on a range of distances and a range of potential source concentrations to develop this nomogram, which allows us to determine PFOA concentration at select distances from known source concentrations. So, as a matter of illustration, the red line here represents a 500 nanogram per liter source concentration. If we back up a step, you'll note that all of the colored lines represent different source concentrations. So starting in the bottom left with the blue line and blue squares represents a source concentration of 50 nanograms per liter, and the green line with green squares towards the top right represents a source concentration of 1,000 nanograms per liter. And again, we're dealing with PFOA as an example. And the colored lines in between represent intermediate source concentrations. Perhaps these source concentrations are known, or perhaps they're inferred. But in any case, as I started to show before, here's an example. So the red line represents a 500 nanogram per liter source concentration for PFOA. And if we wanted to estimate what type of PFOA concentration we could expect 800 feet from that source of 500 nanograms per liter, we could pick off 100 nanograms per liter PFOA concentration. So backing up, we 500 nanogram per liter source concentration. We're interested in what we could expect the concentration to be 800 feet from the source. Perhaps we don't have a monitoring well network. Perhaps we have a supply well or a receptor at that distance, and we want to have some idea of what the PFOA concentration could be. So if our empirical relationship holds, we would expect a PFOA concentration of about 100 nanograms per liter, 800 feet from a source, with a 500 nanogram per liter PFOA source concentration. So we can recast that nomogram in a different way, shown here, and this will show distance to the criterion from known source concentration. So in this instance, you may want to know at what distance from a source concentration would I achieve a groundwater standard. So here, the blue line with the blue dots represents New Hampshire's 12 nanogram per liter ambient groundwater quality standard for PFOA. And if I, again, had a 500 nanogram per liter source concentration of PFOA, or assumed that I had one, and I wanted to know at what distance from the source, would I attain or achieve that 12 nanogram per liter ambient groundwater quality standard, I could pick it off the graph, and it would be approximately 1,800 feet from the source. So just rewind and go through that again. So the blue line represents the 12 nanogram per liter ambient groundwater quality standard. And let's say I have a 500 nanogram per liter source concentration. I want to know, at what distance could I roughly expect to attain that standard, and it would be about 1,800 feet. So we can replicate this diagram for a variety of groundwater criteria or drinking water criteria. So in this instance, we basically show the ambient groundwater quality standard in red of 12 nanograms per liter. The yellow line and triangle is the EPA's health advisory level of 70 nanograms per liter. And the green line represents 10 times the ambient groundwater quality standard of 120. So we can see, we're sticking with an example source concentration of 500 nanograms per liter PFOA, if our groundwater standard was 120 nanograms per liter, or 10 times what's been promulgated in New Hampshire, we would attain that standard at 713 feet. So looking at the health advisory level, again, 500 nanogram per liter source concentration, we'd expect to attain the health advisory level at 983 feet. And lastly, for the actual groundwater quality standard, if we had a 500 nanogram per liter source concentration, we would expect to attain that standard at about 1,800 feet. So again, this is based on that empirical function of 15 samples for 4 sites that I think holds up pretty well, but it is relying on that relationship. But even if it's not perfect, I think it does give you a good sense of the distances to attainment from a particular source concentration. And it also helps illustrate the sensitivity of that distance in groundwater to attain a standard, especially as regulatory criteria change and as they get more and more stringent. Even if you don't know the exact distance, it still puts you in the ballpark to understand some of the implications of these changing and more stringent regulatory criteria. So we can take that last example and transfer it to a real world situation. So here I have an example flow net and a source, and I'm animating our flow line here. And what pops up on the screen are the distances from that source on a real flow net where we'd expect to attain those criteria. So in a practical way, this is important, especially if there's supply wells in the area, or we want to know where to intelligently place our monitoring wells. So we may have a supply well, down gradient from our source, and we would want to know, we may want to assess or predict, where we would attain a regulatory criterion before reaching that supply well. And in the absence of any groundwater data or monitoring well network, we could also use this type of analysis to intelligently place our monitoring well locations, and to do that more efficiently, as opposed to what I call the poke and hope approach. So let's cover the last segment of the presentation and look at the statistical distribution of PFAS relative to regulatory criteria. So what this graph shows is the PFOA concentrations for the entire New Hampshire database for PFOA concentrations of 1 nanogram per liter and higher. And these data are organized from the highest concentration in the data set on the left-hand side, 52,000 nanograms per liter, to 1 nanogram per liter on the far end of the diagram to the right. So this basically is the PFOA concentration for every sample in the New Hampshire database for PFOA concentrations 1 nanogram per liter and higher. And what it shows is there's a pretty large spike on the left-hand side, and a long tail of relatively low concentration, but still above the regulatory criterion. So when you look at and inspect this data distribution, only 13.7% of the samples correspond to 99.8% of the upper concentration range. So 99.8% of the concentration range is represented by only 13.7% of the samples. However, a fairly large percentage, 42.1% of the samples, represents only 0.2% of the concentration range. And all those samples are above the regulatory criterion of 12. So all of that 42% of samples occurs between 12 nanograms per liter and 10 times 12 nanograms per liter, or 120 nanograms per liter. So again, a long tail of relatively low concentration that are still above standard. We can look at this data on a log scale, which helps you see it better. And that's what we're presenting here. So the concentrations are presented on a log scale, but flipping back, I think this is really the more relevant way to look at it, because again, it shows that most of your concentration range is great, corresponds to a small fraction of your samples. So let's look at this on a mass basis. So the intent of this graph is to show that most of the PFAS mass corresponds to a small volume of water. So I think this graph requires a little explanation. So from right to left on the graph progressively sums the concentrations of samples from highest to lowest. And if we assume that if we assume a 1 liter aliquot per sample, this graph represents the cumulative mass of PFOA for all 7,401 samples in the database, meaning that 100% on the left-hand side of the graph corresponds to the sum of PFOA for all 7,401 samples, again, assuming a 1 liter aliquot per sample. And it is used to represent the mass distribution of PFOA in New Hampshire groundwater with bias towards sampling sites, or we could use this to represent the mass distribution of PFOA at any individual site. So when we look at it, we realize that 90% of the mass corresponds to samples that are 120 nanograms per liter or greater. So 90% of the PFOA mass in all of these samples corresponds to samples that are 10 times the regulatory criterion or greater. Only 8.3% of the mass corresponds to the tail here, which is between and still above the regulatory criterion of 12, but less than 10 times that regulatory criterion. So I think it begs the question, if you could get 90% of the PFOA mass out of the ground at any particular site, or out of all of the groundwater in New Hampshire, would it be worth it if you still left behind concentrations over a significant volume of water that were up to 10 times the regulatory standard? So the point is, all the mass, most of the mass is concentrated in a small volume of water, but there's a large volume of water that still has PFOA above the regulatory criterion. So I think this presents some practicability considerations. So with that, let's take it to the conclusions. So PFAS, in this case represented by perfluoroalkyl acids, and we relied heavily on PFOA in our example, may exhibit predictable concentration versus distance function. This can be useful for estimating attainment distance in groundwater or receptor vulnerability. As I said, it might not be perfect. There's some variation in that empirical function, but if you want to get in the ballpark and in the absence of data, understand where you might want to place your monitoring wells, or at a high level determine whether a receptor might be at risk, I think the data that are available to us can be really useful for that. The attainment distance is sensitive to different regulatory criteria. So we showed that a 10 times more stringent regulatory criterion results in a 2.6 greater distance, 2.6 times greater distance to attainment. So few samples, 13.7, corresponded to most of the upper concentration range, and many samples, 42.1%, comprise the low end of the concentration range. So again, a relatively long tail, relatively low concentration, but still above standard. And we showed that most PFAS mass occurs in a small volume of groundwater. And even if you remove 90% of the mass, which I think would be very beneficial and in itself might have some practicability limitations, you would still leave a large volume of water with PFAS concentrations above criteria, as high as 10 times above criteria. And again, a large volume of groundwater includes PFAS concentrations up to 10 times the regulatory criteria, the point I just made. And these distributions present practicability limitations for attainment or remediation of distal portions of PFAS plumes in groundwater. So thank you for your attention to that presentation. And at this point, I will turn it over to Kristen Thoreson of REGENESIS.
Great. Well, thanks so much, Jeff, for presenting here today and for showing that data. I think it's a really great visual of, as you mentioned, this large data set that is out there. But I like how it's coming together to really, I think, help make decisions. As you mentioned, that there's some practicality issues here, and I think that segues nicely into the last portion of this webinar today, which we'll talk about. And I think, again, that data could probably help go about thinking through this type of approach or where it's most applicable, and that is using colloidal activated carbon for in situ PFAS remediation. So I'm going to describe this approach and answer a couple of common questions that come cross with it as well. So Jeff did a good job, I think, of really describing this challenging problem that's associated with PFAS in general, the vast nature of these plumes that can be created, in the sense that they often can expand over thousands of feet and still be above the regulatory limits. Obviously, the concentrations change greatly across that range, but generally they are quite low levels, and we're going after low target levels. And so it does bring up the question of what can be done right now. Obviously, if we do nothing, the problem continues, and we may already have places where there is a risk being posed to these sensitive receptors. But our toolbox is rather empty. We don't have a lot to reach for due to the recalcitrant nature of these compounds. Pump and treat is certainly an option and can be implemented, but often it doesn't align well with this type of a plume, and it can be rather cost ineffective and not very sustainable when we think about the nature of these sites. And so the remedial approach that we have been implementing over the last few years, and what I'll discuss today, is this plume management solution of enhanced attenuation. The simple overview of this approach includes installing an injectable permeable reactive barrier of colloidal activated carbon in the path of this contaminated water. And again, using Jeff's data, it might be useful to think about where you put this barrier, whether it's closer to the source or farther down, to again be most cost effective. So I can see that data being very useful here. But the goal is to get that activated carbon in the path of these contaminants and significantly increase the retardation of those contaminants. So really remove them from groundwater and slow the migration greatly. We've got data, it depends on the site, of course, and the exact contaminants that are present and how much carbon you're putting in. But this, single application can typically last for years, decades at a time. So it's definitely a long-term slowing of the migration over time. In that sense, we're attenuating the plume. The definition of enhanced attenuation coming from ITRC is shown here, and again, that describes this process really well. It's sustainable in that a single application with no ongoing operation and maintenance costs can be implemented, and it's manipulating a natural attenuation process. So there is already natural absorption occurring between these contaminants and the FOC present, but by adding activated carbon, we're essentially supercharging that FOC and really increasing that absorptive property, with the result is that we greatly reduce the mass flux of contaminants with the goal of preventing further migration. Sometimes we call it sequestering, but it's really containment strategy to keep it in place and again prevent the enlarging of the problem. So a number of common questions come up with this approach. The first one often is the idea that there is no destruction happening here. It's absorptive property only. So how does this fit with the scope of remediation? I think it's helpful to look at the definition of remediation to answer this question, where we see that it really comes down to having a process that can eliminate the risk that comes from the exposure to these harmful chemicals. So another way to write that is in the form of an equation. We can write it out as the risk is equal to the product of the hazard times the exposure. So when you write it this way, you can really see that if you can address the hazard or address the exposure, drive either of those down to zero, you have a good way of addressing and decreasing the risk greatly. And this is in line with guidance that has been put out by the EPA over the years, where they have described a couple of different processes or methods to reduce the risk. And those first two listed there really are about addressing the hazard, trying to eliminate or remove the hazard to address the risk. And then the third point, reducing the contaminant mobility and bioavailability, is really going after that exposure. And typically that's done through absorptive or stabilizing type approach. And that is exactly what this approach of using colloidal activated carbon is doing here. By absorbing PFAS to the activated carbon, we're removing it from the groundwater, which reduces the mobility and the exposure pathway. So really not something that's new. Perhaps it's a new way of thinking about it as it pertains to PFAS, but it's something that has been done over the years for other recalcitrant compounds, metals, things that we just really can't degrade and address the hazard very easily. And more recently, I think this is, coming into light. There's some precedent for this. A paper came out at the end of 2021 that started to describe, it's really kind of a nice guidance on how to think through a site if, monitored natural attenuation is appropriate, and if there's potentially a need to enhance monitored natural attenuation, possibly with the use of absorptive compound like a activated carbon. So, this aligns well, and I think is a good kind of background or guidance for this strategy. A second question that comes up is, can you effectively implement a colloidal activated carbon barrier? Obviously, this is a really important aspect. We're essentially trying to build a fence of activated carbon in order to capture those contaminants from moving farther down gradient. And if that is not implemented properly, it's not going to be a very effective strategy. So to answer this question, it really comes down to first having a technology that allows us to get it into the ground. Plume Stop is the technology we're using. We developed about 10 years ago, and it was really with that goal in mind. We wanted to be able to inject a form of activated carbon into the ground, and so that's what we set out to do here. In its simplest form, it is a form of activated carbon and that it's a good absorbent. The key to it being that its particle size is 1 to 2 microns, which is what allows it to fit through the pore throats and distribute readily. There's some other advantages to having the small particle size, but really that's the essential part for the distribution aspect of it. There's some other additives in there too that keep it from agglomerating and clumping together and help it move within the soil subsurface. But the goal is really to have it distribute under low pressures to ensure that we can get really good contact with the water and the contaminants that are fluxing through the zone. And I think this key attribute of distribution is really best described in these gravity columns. So there's no pressure being applied here. These are a mixture of sand, silt, and clay, which is typically a little bit harder to get solid particles through. And just to give you a sense here, it's compared to a commodity powdered activated carbon, which is just generally too large to fit through, so it's filtered out readily on the right side, versus the Plume Stop, which readily passes through the soil and distributes nicely without, again, pressure having to be applied. Now, a fine point, a very, very key fine point to this is that we want it to distribute, but it can't distribute forever. We don't want it to continue flowing with the groundwater far down gradient. And so after the activated carbon was applied here, we actually flushed these columns with clean water. And you can see that there's a staining of the soil. And so that is another aspect of Plume Stop, is that it distributes, but while it's distributing, it's actually interacting and adhering to the soil surface. And so in that sense, it's going to stay in place and it's not going to distribute forever. It's going to help us build that barrier and not continue to move down gradient. The goal with any kind of injection, which is usually through direct push or injection wells, is to target the flux zones. We want to put the Plume Stop, put this colloidal activated carbon in the same zones where the water is moving, where these contaminants are flowing, and how these plumes are being developed, so that we get good contact and can intercept those contaminants. So this is all fine, kind of on paper is looking at it, but obviously what it comes down to is being able to implement this in the field. And so we have a team who's out implementing Plume Stop in the field, our remediation services team, and they have a number of quality control steps that they're taking for every site, because every site's a little bit different, to ensure that the distribution is meeting the intended goals and getting a complete distribution to build that fence. And so, for example, this is a site where the target treatment zone was from 15 to 27 feet. So in that case, these two cores should be completely black, as well as the top of that. And while we are seeing some distribution in this area, it's certainly not to the full extent that was targeted. And so they're in constant contact with our technical team who designed this and making adjustments, real-time adjustments in the field to get the distribution up to where it needed to be. So after making those adjustments, they go back and take some cores and are now seeing that targeted zone being implemented. So this is a really important aspect to being able to successfully implement that barrier. It's having, the tools and the team to be watching this and doing those quality control procedures to ensure the distribution is occurring as we need it to be. In addition to cores, there's also a number of water samples that can be taken to really do the same thing, just to ensure that we're getting the type of distribution needed. These could be taken from monitoring wells or piezometers, again, just to be continually monitoring the distribution over time. And then the final question really comes down to how long will the treatment last? It's not degrading, and especially if there's a infinite source, there is a limited number of absorption sites, so this barrier would fill up. And so our ability to predict the longevity and what all is going to impact longevity is very important when designing this. And we do have the ability to predict longevity because we can calculate retardation factors for specific contaminants with Plume Stop. And that's something that we've done and created over the years to be able to do that. And that's really because Plume Stop behaves like natural organic carbon, but on steroids, in that it is acting to retard the movement of contaminants. And once we have that retardation factor, now we can start to use that in models and start to think about how that translates to time. And so we'll look at that here on this next slide. At first, just as a reminder, this is what the retardation factors are telling us. The groundwater is moving at some distance per time and has its own velocity. And the retardation factors for contaminants is telling us how it's moving relative to that groundwater velocity. So an R1 means it's moving at the same velocity as the groundwater, and an R of 10 would mean it's moving at 1/10 of the velocity as the groundwater. And again, there's always natural retardation factors with the natural FOC that's present, and it depends on the exact species that are present, but typically those are in single digits, double digits, and can range definitely. But when we add activated carbon, again, it's like a supercharged FOC. So for an example, if we have kind of a standard dose of Plume Stop being applied, and in this case, we'll look at TCE as a first example at 100 micrograms per liter. If you assume that we have about a 13-foot long barrier and it's moving at about 250 feet per year, it would take that groundwater about 3 weeks to move across that 13-foot zone. But the retardation factor that the activated carbon creates on that TCE is a factor of about 600. So now the time it takes a TCE to move across that zone is about 30 years. Again, we have the retardation factors calculated for PFOA as it relates to Plume Stop as well. And if we drop it down to concentrations that are more typical of PFAS, which I think are in line with some of the ones that Jeff described, now that retardation factor increases even more. So again, we're talking about many, many years for it to translate across that. Now, these are relatively simple examples without other factors being imparted on it. And obviously, the longevity prediction is more complex at any given site when there are more than one species present and other site-specific factors are considered. So to help with that, we developed a model that can take all those factors and roll them up and give us a predictive output on longevity. This will take into account, again, multiple species that may be present, what the actual contaminant mass flux is moving through that barrier. That's really an important term. If there are any other non-target compounds present, as those can and will absorb to the activated carbon as well. And then this can all be taken into and kind of calculated what the competitive absorption is going to look like. So we know how those species will move through the zone. And then we can also start to take into consideration the carbon dose, what the barrier thickness is, what the amount of time that it's going to translate to. And this, again, it gives us a predictive output of what a dose will last and how we might adjust that to meet the needs of the site. And also just mention that the longevity can also greatly depend on what is occurring at the source. So if there's an infinite source, then there's going to be an ongoing amount of contaminant flux coming into that zone, and that will certainly affect longevity. But if the source has been, if some kind of source control measure has been taken, so perhaps if a lot of the contaminant mass is in the vadose zone and that's been stabilized or removed or capped or some way, then we may actually have a decreasing source input, and that's going to help extend the longevity of that barrier. And even in some cases, a single application may suffice, and that you might not have to go back and put in another barrier down the road. And there's, I put a QR code here that takes you to our PFAS Resource Center, but there's a great video, a technical video that kind of describes this process as it relates to how a barrier may last, getting into details of isotherms, and just a lot of more technical discussion on that. So I'd welcome you to go there if you want some more information, as well as just a lot of other information on case studies and whatnot related to how Plume Stop is being used to address PFAS. And I'll close here with just giving a sense of, how this is being implemented. At this point in time, there's, I think, close to 30 sites where Plume Stop has actually been applied in pilot or full-scale sites to address PFAS. And there's a very large number that are in the design and review phase, getting ready to go down the road, or looking at the feasibility of how this might be applied. And this summarizes the types of sites where we have applied Plume Stop to address PFAS. So nothing too surprising here, because most of these are sites that are commonly associated with PFAS. So between the airports, industrial sites, landfills, we're really getting a large suite of different types of sites where this is being implemented, and so we can kind of understand how each one has a little bit different nuance. Many of these have been implemented in the last 6 months to 2 years, so some of these don't have a lot of long-term data, but I will highlight that there are a couple that have been in the ground for a little bit longer, which is typically a question we get on, what kind of long-term data do we have. So the Michigan Army Airfield site, Camp Grayling, is one that we have data for over about 3.5 years now, where concentrations have remained non-detect since first implementing. And then this Ontario industrial site is another one where we have 5.5 years now, where again, concentrations have remained non-detect since the initial application. So while there are many new sites going in there, there are some longer term data that where we're continuing to collect to show how this can continue to work over time. So with that, I'll just close this out by hopefully showing that we have Plume Stop as a cost-effective, long-lasting strategy to manage PFAS. And a key part of that is having the ability to install these barriers with a lot of quality control steps that are performed to confirm the barrier installation. And I didn't have time to get into this, but we'd certainly be happy to talk to you if you have questions on this. But all of the experience we have with Plume Stop and how we can design these and have confidence in our ability to put together a good design, we actually are offering a extended warranty for these types of barriers where Plume Stop is being used to address PFAS. So in that sense, we will assess a site and implement the barrier and keep monitoring it for 10 years. And if at any point the standards are not being achieved related to that site, we'll go back out and fix it. And so again, we're happy to talk through that program with you, but we know that this one's, with PFAS and the inability to degrade, it's essential to get that barrier installed. And again, we're confident in that ability to do that, and we'll stand behind it with this extended warranty. So with that, we'd be happy to take any questions that you have for myself or Jeff. And again, just want to thank Jeff for his presentation today and coming on here to talk about some really interesting data analysis.
All right, thank you very much, Kristen. That concludes the formal section of our presentation. So at this point, we'd like to shift into the question and answer portion of the webcast. Before we do this, just a couple quick reminders. First, we will be sending out a brief survey after the webinar. We really appreciate your feedback, so please take a minute to let us know how we did. Also, you will receive an email with the recording as soon as it is available. All right, so let's circle back to the questions here. This is a question for Jeff. Jeff, the question is, what are the strengths and limitations of an empirical model to represent multiple PFAS sites?
Well, we know that PFAS data are proliferating. We're sampling more and more for PFAS, and allowing fate and transport to be assessed using real data versus say prior speculation about fate and transport characteristics of PFAS. I think we've come to understand the characteristics of PFAS, fate and transport. It's been somewhat speculative in a theoretical way, but now we're really getting a lot of data that can kind of ground truth that and allow us to understand how PFAS plumes are really migrating. This empirical approach is not affected by site-specific biodegradation rates, which complicates a site-to-site comparison for other chemical constituents. So benzene would experience biodegradation at most sites, but perhaps at different rates. So that's a beneficial process, but it's hard to lump them all together and understand benzene migration across a lot of sites empirically. But the limitations are that it requires similar sources, similar release history, and similar physical setting to be applicable to a particular site. So this could be accomplished using, say, type curves, for instance, of a common set of conditions. So maybe you have a model for the end-of-life cycle waste facilities in a particular physical setting like we showed today. Maybe you have a model for fire training areas at Air Force bases and glacial outwash setting. So I think those are some of the strengths and limitations of this approach.
All right, thanks, Jeff. So here's a question. This one is for Kristen. And Kristen, the question is, can non-target compounds block adsorption of PFAS compounds to the colloidal activated carbon?
Yes, I think the simple answer is yes. I might describe it, certainly could be described as blocking. It might be more of a competitive nature, is that sometimes non-target compounds can outcompete the PFAS. And that's an essential thing for us to understand. Again, that's part of why we are always interested in having as much data as we can. I think I mentioned having like TOC data, especially if it's a landfill site, because that will adsorb to the activated carbon and will impact the overall longevity. But it's something we can factor in and design for as needed. So yeah, I mean, it's essential to know that. I guess another aspect is when we're asking for as much data as possible is that sometimes we do want to know what the target contaminants are. But if there is a longer list of analytes that have been observed at that site from any kind of upgradient well, that's really helpful, again, because then we just have a better understanding of the total mass of organic contaminants that might be organic contaminants or non-contaminants, just other species that are coming into that zone that will take up adsorption sites.
Okay, thanks, Kristen. So this is another question. This one's for Jeff. And the question is, how can this approach be used to guide site investigations?
So this approach of using empirical data to project the extent of your PFAS plume, it's not perfect, but I think it puts you in the ballpark, allowing for intelligent placement of monitoring wells in lieu of what I call the poke and hope approach to site investigations.
All right, thanks, Jeff. So let's see here. So this is, we have another question here. This one's for Kristen. Kristen, the question is, this may be hard to predict, but do you expect that a destructive technology could be implemented with Plume Stop?
Yeah, sure. I'd say that's always the hope, right? What we do for other contaminants like chlorinated solvents or petroleum hydrocarbons is that we typically will co-apply Plume Stop with another technology that can destroy it, and in that sense make a very reactive zone where the contaminants are slowed but then have plenty of time to react with the destructive technology. I am certainly hopeful that after some amount of time we will have destructive options for PFAS, and in that sense it could follow with what we're doing with others, that we can really concentrate the PFAS in the zone and then go in with the destructive technology to actually remove them over time. So I don't see why that wouldn't work for PFAS in the same way that it's worked for other contaminants, and I am definitely hopeful that we can do that in the future. And in a lot of ways, that's a way that people look at this approach is that it's almost a buying time approach, that we can concentrate and prevent further migration of PFAS right now in these barriers, know exactly where it is, and then we'd have the ability to go back and destroy them later with anything that might be developed in the coming years.
All right, thank you, Kristen. So this is another question for Jeff. Jeff, the question is, how can this approach be used to assess receptor vulnerability?
Well, in the absence of monitoring well data, this approach allows for a preliminary assessment of whether receptors could be affected based on proximity to PFAS sources. So I think, this type of preliminary or high-level assessment is useful to water resources managers, private supply well owners, as well as, responsible parties who are looking to assess and manage their liabilities in the absence of data.
Okay, thanks, Jeff. We have another question here. Kristen, this one's for you. It is, if Plume Stop did get into surface water, is there any concern for aquatic organisms?
Yeah, that's a good question. One we certainly have been asked before. And again, obviously our goal is to not have it ever reach surface water, because we do have a good understanding of how it's going to transport, and we can, put these barriers in a place where that's not going to happen. Obviously, sometimes you do want to be quite close to the interface between groundwater and where surface water might be. But I guess the good news is that we have gone on the road of testing this. We've done some acute toxicity testing with Plume Stop to ensure that that will not be harmful to any aquatic organisms, and had results that show that there's no toxicity effect in that case. So we can be confident that there won't be any kind of issue there at all.
Thanks, Kristen. So here's another question for Jeff. Jeff, the question is, can you recommend a remediation paradigm given these practicability limitations?
Sure. So the distances to attainment that have been demonstrated and the volume of water containing, a small mass above criteria presents practicability limitations. So to me, this points to a three-pronged approach. The first prong being remediation criteria achieved with source treatment, removal, or control. So specific remediation criteria, perhaps it's like we looked at in the presentation, 10 times the health protective criteria that corresponds to 90% of the mass. Perhaps that's your remediation criterion that's applied closer to the source through source treatment, removal, or control. Next, we still need receptor protection. What's driving these criteria lower and lower, is health protective considerations. So perhaps we have a separate criterion for receptor protection, and that's achieved through protective measures. And it might be something that's 10 times more stringent than the remediation criterion. So that leaves us with everything in between. So I think in between, you dealing with a plume management approach involving some combination of monitoring, attenuation, and in situ approaches. And I think that ties in to Kristen's presentation and how to increase sorption, reduce mass flux, and if you can reduce the flux towards that receptor, you're affording it some additional protection, but you may also have the economic benefit, say, of less frequent changeouts if you have a POET system, for instance. So that's how I would approach, when we really understand the distribution of PFAS in the subsurface, I think that's a practicable three-pronged approach.
All right, thanks, Jeff. We have another question here. Kristen, this one is for you. The question is, does the Plume Stop move differently in different types of soils?
Yeah, it does. Those columns that I showed you where it's moving through and it's having that affinity with the soil, it will be a little bit different with different types of soils. So the more clay and silt, you'll have a little bit more sticking to it as it's passing through than if it's more of like a sand or a gravel, which is part of what we look at every site, in the pre-assessment and the pre-characterization phase, is to understand, what is the nature of the aquifer and how might that change how we design, maybe the spacing, what that looks like. But that's, part of the thing that I think we've learned a lot over the last 10 years of having Plume Stop and the experience we came with, is that just how to implement into different types of soils and be strategic about that as needed. So, yes, getting back to the question of, it does certainly move a little bit differently, but it's something that we can, again, look at with each site and predict and make adjustments as needed to ensure that we are getting that distribution and that in-ground fence of activated carbon built appropriately.
All right, thanks very much, Kristen. So that is going to be the end of our chat questions. If we did not get to your question, someone will make an effort to follow up with you. If you'd like to learn more about services from Woodard and Curran, you can visit woodardcurran.com. If you'd like to learn more about remediation solutions from REGENESIS, you can visit regenesis.com. Thanks again very much to Jeff Hale and Kristen Thoreson, and thanks to everyone who could join us. Have a great day.